We start this lecture with an overview, a plan for what will be presented. In this pre-lecture, we will continue our study of oscillatory motion by studying a few specific examples. We will start by discussing the torsion pendulum, in which a disc suspended by a wire through its symmetry axis executes oscillations about that axis. We will find that the frequency of these oscillations is determined by the moment of inertia of the disc and the torsion constant of the wire. We will then investigate the physical pendulum, in which an object hung from a frictionless pivot executes oscillations that are determined by the restoring torque that is provided by the weight of the object itself. We will find that these oscillations can be described as simple harmonic motion as long as the angular displacements are small. The frequency of these oscillations is independent of the mass of the object, being determined just by the size and shape of the object. Last time we showed that an object that is subjected to a linear restoring force about some equilibrium position will oscillate around that equilibrium position, executing simple harmonic motion. The specific system we studied was that of a mass attached to a fixed spring, and we discovered that the oscillation was sinusoidal, and the frequency of the oscillation did not depend on the amplitude of the oscillation, but only on the mass of the object and the stiffness of the spring. Are there other systems that display similar behavior? The answer, of course, is yes. Simple harmonic motion is ubiquitous in all of nature and can be found everywhere, from systems of atoms to systems of galaxies. We can identify a system that will exhibit such behavior if we can reduce the equations that govern its motion to the signature differential equation for simple harmonic motion that we derived last time. In this pre-lecture, we will once again use Newton's second law to identify several systems that exhibit simple harmonic motion. Here we see a disc suspended by a vertical wire attached to the center of the disc, parallel to its symmetry axis. The other end of the wire is attached to a fixed support. A rotation of the disc about its symmetry axis causes the wire to twist. Once twisted, the wire exerts a restoring torque on the disc. The magnitude of this torque is proportional to the angle through which the disc has been rotated. The direction of this torque is such that it causes the disc to return to its equilibrium position. If the disc is rotated through some initial angle and released, it will oscillate back and forth, executing simple harmonic motion. We can analyze this motion by applying Newton's second law for rotations. Writing the angular acceleration as the second derivative of the angular displacement, we obtain the signature differential equation for simple harmonic motion. We identify the angular frequency of the motion as the square root of the torsion constant divided by the moment of inertia of the disc about its symmetry axis. We can now see from this equation of motion that the torsion pendulum is the rotational analog of the mass on a spring system. The roles that displacement, force, mass, and the spring constant play for the mass on a spring system are played by the angular displacement, the torque, the moment of inertia, and the torsion constant in the torsion pendulum. The general solution for the angular displacement of the pendulum as a function of time, therefore, has the same sinusoidal form as that of the displacement of the mass on a spring. Another class of systems that exhibit simple harmonic motion is that of pendula, objects that are supported from a pivot that have a restoring torque provided by gravity. We have already seen that the weight of an object, hung from a frictionless pivot, exerts a torque that is proportional to the horizontal displacement of its center of mass away from the pivot. This torque is a restoring torque in that it acts so as to reduce this horizontal displacement. Here we see such a pendulum being pulled back and released. We see it swinging back and forth in a regular way. We will now prove that this system exhibits simple harmonic motion as long as the angle that the pendulum makes with the vertical axis is not too big. We start with Newton's second law for rotations, and we evaluate both sides for motion around the pivot. On the left-hand side, the torque is equal to the weight of the pendulum times the horizontal displacement of the center of mass. The minus sign indicates that the torque opposes the displacement. As long as the angle between the vertical direction and the line connecting the pivot to the center of mass isn't too big, we can approximate the horizontal displacement by the arc length, as shown. With this approximation, we can write the displacement in terms of the angle and the distance from the pivot to the center of mass. The right-hand side of the equation is equal to the moment of inertia times the second time derivative of the angle, just as it was for the torsion pendulum on the previous slide. We have now obtained the signature equation for simple harmonic motion with the angular frequency equal to the square root of the product of the weight of the pendulum and the distance of its center of mass from the pivot, divided by its moment of inertia about the pivot. The variable that executes simple harmonic motion is the angle between the vertical direction and the line connecting the pivot to the center of mass. On the next slide, we will examine the simple pendulum consisting of a mass at the end of a string. Here we see a simple pendulum, a point mass M attached to a massless string that is suspended from a pivot. We can apply our results from the last slide with the distance from the pivot to the center of mass being equal to L, the length of the pendulum, and the moment of inertia equal to ml squared. The angular frequency of the motion, then, is equal to the square root of the acceleration due to gravity divided by the length of the pendulum. The period of the motion is, as always, given by 2 pi divided by the angular frequency and is therefore proportional to the square root of the length of the pendulum. To get a feeling for the magnitudes involved, we see that the period of a pendulum whose length is 2 meters will be a little under 3 seconds. Now, 2 meters is a typical distance between you and the crossbar when you sit on a playground swing. Consequently, it makes sense that it takes you a few seconds to swing back and forth on a swing. Since the period doesn't depend on mass, it also makes sense that people having different masses can swing back and forth on a pair of playground swings while staying more or less side by side. Just as was the case for the mass on a spring, we can use the initial conditions to determine the angle of the string as a function of time. For example, if we release the pendulum from rest, we know the amplitude will be given by the initial displacement, and the phase of the cosine function will be 0. Before we leave this example, we want to point out a source of possible confusion using the symbol omega. The omega we have used in these equations is the angular frequency of the motion, a constant that does not depend on time. Now, the angular velocity for the mass, d theta dt, which is often denoted also by omega, is not a constant. Indeed, d theta dt itself oscillates with angular frequency omega. We will now replace our simple pendulum by an object having a more complicated shape. Which properties of this oscillating system will be the same as those for a simple pendulum, and which will change? The answer is that the oscillating behavior is exactly the same as before, the only difference being that the expression for the frequency of oscillation will look a bit different, depending on the location of the center of mass and the moment of inertia of the object. For example, here we see a stick of mass m and length L pivoted at one end. The distance from the pivot to the center of mass of the stick is half the length of the stick, while the moment of inertia of a thin rod about its end is given by 1/3 ml squared. Plugging in these quantities, we find that this stick behaves exactly like a simple pendulum whose length is 2/3 that of the stick. Here we see another physical pendulum with a different shape and mass. We know we can find the period of this pendulum from its mass, its distance to the pivot, and its moment of inertia. Since the moment of inertia will always be proportional to the mass of the object, we see that the period will be determined totally by the size and shape of the object. All of the results we have obtained so far for a pendulum oscillating due to gravity have depended on the assumption that the angle of oscillation is small. You may be wondering about this limitation. How small is small? As the angles increase, what happens to these oscillations? We will address these questions a bit more on the next slide. We obtained the signature differential equation for simple harmonic motion for the angular displacement of a pendulum by assuming that the length of the arc swept out by the tip of a vector of length r as it is displaced through an angle theta from the vertical is approximately equal to the horizontal distance moved by the tip of the vector. Now, the exact expression for this distance is equal to r sine theta, not r theta. Had we used this exact form, our differential equation would have looked almost the same, except we would have had sine theta rather than theta on the right-hand side. The upside of this equation is that it is an exact description of our system, valid for any angle. The downside of this equation, though, is that it does not have a simple analytic solution. To answer the question as to how small must the angle be so that the exact solution can be approximated by simple harmonic motion, we just need to look at how well theta approximates sine theta. We can make this comparison simply by using a calculator in its radian mode. Here we see a plot of the percentage difference between sine theta and theta as a function of theta. We can see that the approximation is good to better than 5% for angles less than about 30 degrees. What happens to the motion of the pendulum as we increase the amplitude of the oscillations? The answer is not much, actually. The pendulum still has a fixed period, but a careful measurement of the angle as a function of time would show that the oscillations are no longer perfectly sinusoidal, and a careful investigation of the period of the oscillation would show that it is no longer completely independent of its amplitude. Consequently, we should be aware that the description of the motion of a pendulum as simple harmonic motion is not exact, but that it is, nonetheless, a very good description of the motion for moderate angles of oscillation. We conclude with a brief discussion of the main points of this pre-lecture. First, we discussed the motion of a torsion pendulum, in which a disc, suspended by a wire through its symmetry axis, executes oscillations about that axis. The restoring torque provided by the wire is proportional to the angular displacement of the disc about its axis. Applying Newton's second law for rotations, we found that the disc executes simple harmonic motion with a frequency proportional to the square root of the torsion constant divided by the moment of inertia of the disc about its symmetry axis. Second, we discussed the motion of a physical pendulum, in which an object hung from a frictionless pivot executes oscillations that are determined by the restoring torque that is provided by the weight of the object itself. Applying Newton's second law for rotations, we found that the motion could be described as simple harmonic motion in the limit that the angular displacement of the object from vertical is small. The frequency of oscillations is proportional to the square root of the ratio of the weight of the object to its moment of inertia about the pivot times the distance between the pivot and the center of mass of the object. Since the moment of inertia is always proportional to the mass of the object, we determined that the oscillation frequency is independent of the mass of the object, being determined just by the size and the shape of the object.